This presentation is about improving flood frequency analysis, which is about estimating the occurrence of rare floods, such as on this plot where we are fitting a GeV distribution to records of annual maximum stream flow. And the objective is to estimate the 1 in 10 or the 1 in 100 years flood. The overall fitting process is difficult when streamflow records are short, such as on the plot on the right here, where there's only 10 years of data. In comparison, if I use 110 years on the left, you can see that the uncertainty in the 1 in 100 years flood is much smaller. So we need a process to reduce the uncertainty when there's short streamflow records. And one way to do this is to combine observed streamflow records with simulated data. In Australia, we are fortunate to have a national hydrological modelling service called the Australian Water Outlook, which is based on the AURA-L landscape model, a gridded model at 5-kilometer resolution. And the model provides simulated runoff for the whole continent over a continuous period of 110 years. And that gives us, for any catchment, as the one you can see on the screen here, a continuous annual maximum streamflow series of simulated data for 110 years. Now, if we compare the simulation with the observation at the site, we can see generally there's a reasonably good agreement. It's not perfect, it's a model, but we can use that within a flood frequency context to improve the fitting of univariate GeV distribution. Now, the model we are proposing today is called COFFEE, the covariate-based flood frequency inference, and it combines on the left a GeV fitted on observed streamflow records, and on the right the same GeV distribution but fitted on long simulated streamflow records. And both of them are combined within a statistical model called a copula, which links the frequency of the two. And the overall model is called COFFEE, covariate-based flood frequency inference. And if we compare the performance of the two, so we selected 39 stations in Australia with the longest possible record in the country. We derive a reference distribution using all the data at the site, and then compare the performance when we apply univariate and COFFEE on a very short 5 years randomly selected data set. If we look at the performance on the left of the univariate, meaning a single GeV fitted to observed, we can see the average bias is about 59%, 60%, that's very large. But when we apply the covariate-based flood frequency estimate on the right, that diminishes to 36%. So broadly speaking, we're halving the bias on flood frequency estimates. Thank you.